Welcome back to the deep dive.
Yeah.
Today we're wrapping up our big series on quantum computing. It's been quite a journey, hasn't it? We started with the limits of classical computers, dove deep into the weirdness of the quantum realm, even got hands on building circuits. So now for this final deep dive, we're going to take a breath, look back a bit, but mainly gaze forward. What's actually next? What does the future hold for this really revolutionary technology?
It's a great time to ask that.
Yeah, because the road ahead, it's clearly got huge challenges, right?
Yeah.
But also these incredible opportunities for everyone, science, industry, society.
Yeah.
And you see places like Canada really pushing forward, leading research, actively trying to boom that future.
Mm-hmm. Definitely investing heavily.
So our mission today really is to pull together the key things we've learned, face those big scaling hurdles head on, and look at the new jobs, the research frontiers, and importantly, the ethical questions that are popping up. Okay, so let's unpack this. We figured a Q&A format would work best for this final one, just to keep things clear. We'll kick off with a quick recap of the journey so far, then tackle the major hurdles in scaling these machines. After that, we'll look at the new quantum workforce and research frontiers, then the ethics, that's a big one. And we need to clarify the difference between PQC and QKD, post-quantum cryptography, and quantum key distribution.
Very important distinction, yeah.
Exactly. And finally, sort of the grand vision. What does this quantum age actually mean for how we see the world? So let's dive in. First question, we've covered so much ground. Before we look forward, can you just briefly recap that journey? What were the key steps?
Absolutely. So it really all started with why we even need quantum, right? The fact that classical computers they hit a wall with certain kinds of problems with exponential complexity. And that immediately pushed us into this pretty counterintuitive world of qubits, superposition, entanglement. These aren't just faster bits. They're fundamentally different ways of holding and processing information based on quantum physics itself.
The building blocks.
Exactly. The weird, powerful building blocks. Then we had to grapple with the physics underneath it all. Measurement, probability, the uncertainty principle, the no cloning theorem, things that feel really alien compared to classical physics. But they're crucial because they define the rules of the game, what you can and can't do.
Right.
From there, we moved into the engineering side, quantum circuits, quantum gates, thinking of them as the verbs of this new programming language, all working within this framework of reversible computing, which is also different. And with that groundwork laid, we saw the power of specific algorithms, like Dorch's algorithm, which wasn't just about solving a problem. It proved quantum parallelism, that ability to explore many paths at once. Then Grover's, showing a real speed up for searching unstructured data. Huge implications.
And Shor's.
Yeah, Shor's algorithm, the big one. Its power to factor large numbers, that's the direct threat to RSA encryption, the backbone of so much of our current digital security. It forces a total rethink.
It really changes the landscape.
Completely. Then we got practical with Qiskit, actually programming these things, which is great, but it immediately throws you face first into the biggest challenge: noise. Decoherence. So we looked at error correction, QEC, especially the surface code, which is kind of the leading candidate for making these things fault tolerant, even though it's incredibly demanding.
Right, we'll come back to that.
Yeah. And then we flipped the coin. Quantum doesn't just break codes, it can make them. So QKD, quantum key distribution, like the BB84 protocol, using physics for secure communication, that leads to the vision of a quantum internet. And finally, we surveyed the landscape applications in chemistry, finance, AI, the big companies involved, the different hardware types. It's been a lot.
That's a fantastic summary. It really shows the progress. But okay, even with all that, you mentioned the noise, the errors. What is the fundamental battle we're still fighting against quantum noise? Is it just decoherence?
Fundamentally, yes. It really boils down to decoherence. It's the tendency of a qubit's delicate quantum state to just collapse due to tiny interactions with its environment. Think of it like trying to balance a spinning top perfectly on its point. The slightest vibration knocks it over. Now, coherence times have gotten much, much better. But we're still talking orders of magnitude shorter than what we need for the really complex algorithms, like Shor's on a big number. So the focus for the hardware folks is not just making qubits last longer, but making them more uniform, more reliable, and crucially, reducing crosstalk. That's interference between qubits. You need them isolated, but also able to talk to each other precisely. It's a tough balance.
Right, controlling that interaction. So if decoherence is the fight at the single qubit level, what about scaling up? We hear about this interconnect bottleneck. What does that mean in practice when you go from hundreds to, say, millions of qubits?
Oh, the interconnect bottleneck is a huge physical engineering headache. It's basically the challenge of how you physically wire up and control potentially millions of qubits. Take a superconducting quantum computer, the kind that sits in those big dilution refrigerators.
Or the super cold ones.
Exactly, near absolute zero. Every single qubit in there needs multiple control lines, wires, carrying signals running from room temperature electronics down into that extremely cold, sensitive environment.
Okay, I could see the problem.
Now imagine doing that not for a few hundred, but for 1,000,000 qubits. How do you route millions of tiny wires into that cryogenic space without them interfering with each other, without introducing more heat and noise?
Yeah.
It's a potential wiring nightmare.
Yeah, it sounds almost impossible.
It demands totally new thinking in cryoelectronics, maybe integrating control circuits directly onto the quantum chip itself. That's a whole other level of complexity.
Wow. Okay, another huge hurdle. Now, we talked about powerful algorithms like Shor's, but the sources mention a software and algorithm gap. What's that about? Don't we have the algorithms we need?
We have some powerful algorithms like Shor's and Grover's, but the gap refers to the disconnect between what those algorithms require in terms of qubit quality and quantity and what today's hardware can actually deliver. We're currently in the INSQ era, right? Noisy intermediate scale quantum. Our machines have maybe tens to hundreds of qubits, and they're noisy, prone to errors.
Okay.
Running Shor's to break, say, a standard 2048-bit RSA key, that likely needs millions of high-quality, error-corrected logical qubits. We're nowhere near that yet.
Right, so the gap is between the theory and the current reality of the hardware.
Exactly. So a big focus now is developing new algorithms, maybe less famous ones, that are more resilient to noise. Algorithms that can still give us a quantum advantage, do something useful faster than classical computer, even on these imperfect near-term NSQ machines. It often involved co-design, tailoring the algorithm and the hardware together for specific problems, finding the sweet spot.
Makes sense. And you mentioned error correction, QEC, and logical qubits. The sources really emphasize the immense cost of QEC. You said maybe thousands of physical qubits for one logical one. Why is that overhead so massive?
It's massive because qubits are so fragile. The leading approach, the surface code, essentially uses a large grid of physical qubits to redundantly encode the information of a single, more stable logical qubit. Think of it like having many unreliable messengers carry parts of a message, hoping that even if some get it wrong, you can piece together the correct message from the majority.
Okay, redundancy.
Exactly, but on a huge scale. Estimates, they range from maybe 1,000 to potentially tens of thousands of physical qubits, just to create and protect one logical qubit from errors.
Tens of thousands for one.
Yeah. So if you need a machine with, say, a few thousand logical qubits to do something truly world-changing, well, you do the math. You're talking about a processor with potentially tens of millions of physical qubits.
That's staggering.
It is. And it's not just the number. You also have the challenge of constantly measuring these physical qubits to check for errors, reading the error syndromes, and then correcting them in real time, which is itself a massive classical computing task running alongside the quantum one.
So it's a hurdle squared, almost.
You could say that. While the surface code is the front runner, people are looking at other error-correcting codes and ideas like topological qubits, which might be naturally more robust. But yeah, the overhead is currently the dominant challenge for fault tolerance.
Okay, despite these, frankly, daunting challenges, the field is clearly moving forward. It's creating buzz, investment, and jobs. What kind of new jobs and careers are actually emerging from this quantum push?
Yeah, that's one of the really exciting aspects. There's a growing demand for what you might call quantum-ready professionals. It's creating these new roles that sit at the intersection of physics, computer science, and engineering. So you've got quantum hardware engineers. These are the people actually designing, building, testing, improving the physical machines, the fridges, the lasers, the chips themselves. Deep physics and engineering knowledge needed there.
Makes sense.
Then quantum algorithm designers. These are often PhD-level researchers figuring out new ways to use quantum mechanics to solve problems, inventing the next Shor's or Grover's, or maybe algorithms for specific applications. Closely related are quantum software developers. They're the ones using frameworks like Qiskit or Cirq or PennyLane to actually write the code, build the software tools, the compilers, the interfaces that let us run these algorithms.
So translating the theory into practice.
Exactly. And then a really crucial role emerging is the quantum application scientist or consultant. These are people who might be experts in, say, chemistry or finance or logistics, but they also understand enough quantum computing to see where it could apply in their field and how to translate those industry problems into something a quantum computer could potentially tackle. They bridge the gap.
That bridge role sounds critical.
It really is. And you see countries like Canada, as you mentioned, investing heavily in universities and training programs, places like Perimeter Institute or IQC, to build up this specialized talent pool. Because the best hardware in the world is useless without people who know how to use it.
Absolutely.
Yeah.
Okay, so beyond the immediate jobs, what about the fundamental research? What are the big open questions or frontiers that scientists are still exploring?
Oh, there's still so much fundamental work going on. One huge area is searching for novel qubit modalities. Are there better ways to build qubits than the current main approaches like superconducting circuits or trapped ions? People are exploring things like photonic qubits, neutral atoms, diamond vacancies, and the sort of holy grail for some, topological qubits, which theoretically could be much more resistant to noise.
So looking for inherently better building blocks.
Right. Another major frontier is connecting quantum computers. How do we build the infrastructure for a true quantum internet? How do we reliably entangle qubits over long distances? This would allow linking smaller, specialized quantum processors together into a more powerful distributed system, or enabling things like secure quantum communication globally.
A quantum cloud, almost.
Kind of, yeah. And then there's quantum-enhanced sensing. Using the extreme sensitivity of quantum states to build sensors far more precise than anything classical. This could revolutionize things like medical imaging, better MRIs maybe, navigation, geological surveys, even detecting gravitational waves, using quantum not just for computing, but for measuring the world with incredible fidelity.
Fascinating. But this incredible power, as we've hinted, it comes with responsibility. Let's shift to the ethical side. What's the most urgent ethical issue related to cryptography that quantum computing presents?
Without a doubt, the most urgent issue is the cryptographic threat. The fact that a large-scale quantum computer running Shor's algorithm could break the encryption standards like RSA and ECC that protect almost all of our current secure communications and data, that's a profound threat.
Right.
And the real urgency comes from this harvest now, decrypt later problem. Adversaries, maybe nation states, could be capturing encrypted data today, storing it, and just waiting until they have a powerful enough quantum computer to decrypt it years down the line.
So secrets from today could be revealed tomorrow.
Exactly. That makes the development and, crucially, the deployment of post-quantum cryptography, PQC, an incredibly urgent ethical imperative. We need to transition our digital infrastructure to these new quantum-resistant algorithms before a capable quantum computer arrives. The clock is ticking on that one.
That's a stark warning. Okay, related to that power, what about access and equity? Is there a risk that quantum computing just widens the gap between rich and poor, powerful and less powerful?
That's a huge ethical concern, yes. Quantum computers, at least for the foreseeable future, are likely to be incredibly expensive and complex machines. There's a very real risk that access to this transformative power could be concentrated in the hands of a few wealthy nations or large corporations. This could absolutely exacerbate existing global inequalities, creating, quantum haves and quantum have-nots. So thinking about how to ensure broad, equitable access, maybe through cloud platforms, international research collaborations, open source software is really critical. We need proactive efforts to democratize this technology as much as possible.
Yeah, preventing a quantum divide. Now, our sources use the term dual-use technology for quantum computing. What does that mean, and what kind of dialogue does that necessitate?
Dual use just means it has the potential for both significant civilian benefits and military or harmful applications, just like nuclear energy or AI or even chemistry.
Okay.
So while quantum computing could revolutionize medicine or material science, its power in optimization and simulation could theoretically also be used to design more effective weapons, break codes for espionage, or perhaps create new forms of surveillance.
Right, the flip side of the coin.
Precisely. And because the potential impacts are so profound, it really demands a global conversation about responsible governance now. We need international dialogue involving scientists, policymakers, ethicists, and the public to think about potential misuse and establish norms, guidelines, maybe even treaties to steer development in beneficial directions and mitigate the risks. Waiting until the technology is fully mature is too late.
That seems wise. Okay, let's clarify those security terms again, because it's easy to get them mixed up. What is the fundamental difference between quantum cryptography, like QKD, and post-quantum cryptography, PQC?
It's a really important distinction to keep clear. Quantum cryptography in QKD is the main example, actively uses quantum mechanics to achieve its security goal. So QKD uses things like single photons and their quantum properties, like polarization, to allow two parties to generate a shared secret key in a way that, according to the laws of physics, any attempt to eavesdrop inevitably disturbs the system and eludes the users.
So it uses quantum phenomena directly for protection.
Exactly. It uses quantum to protect. And crucially, it requires specialized quantum hardware, single photon sources, detectors, quantum channels. Post-quantum cryptography, PQC, on the other hand, is completely different. It refers to new classical algorithms. These are algorithms designed to run on the computers we already have, our laptops, servers, phones.
Okay, so no quantum hardware needed for PQC.
Right. The key thing about PQC algorithms is that they are based on mathematical problems believed to be hard for both classical computers and future quantum computers to solve. They're designed to resist attacks from Shor's algorithm, for instance. So PQC is essentially a software upgrade for our existing systems. It defends against quantum attacks.
Got it. Uses quantum versus defends against quantum. That's helpful. So in practice then, what role does each play? What does PQC do and what does QKD do?
PQC's main role is to be that software upgrade for the vast majority of our digital infrastructure. It's about replacing current vulnerable algorithms like RSA with these new quantum-resistant ones, protecting everything from websites and VPNs to digital signatures and stored data. It's the broad, scalable defense. QKD, needing that special hardware, is more suited for securing specific, high-value communication links where you need the absolute highest physics-based guarantee of security for key exchange. Think maybe secure links between government agencies, critical infrastructure control systems, or high-security financial transactions. It provides a different, arguably stronger, but less broadly applicable layer of security.
Okay, so PQC for the masses, QKD for the highest-stakes links, perhaps?
That's a reasonable way to think about it, yeah.
All right. We're nearing the end of this journey, both in this deep dive and our series. Standing here today looking at everything, what's the big story of quantum computing? And what's the key takeaway you want people to have about its future?
The story, I think, is really one of human curiosity pushing boundaries. It started with just trying to understand the weirdness of the quantum world, fundamental physics. And that led, step by step, to realizing we could harness that weirdness for computation, for information processing, in a totally new way. It's a journey from deep theory to the verge of a new technological reality. Now, the path ahead, as we've discussed, it's steep. There are huge challenges at decoherence, scaling, error correction. But I'd say the summit is now in view. We can see the path, even if it's hard. And the fact that we are seeing a quantum workforce emerge, new research frontiers opening up, these serious ethical discussions happening that tells you the field is maturing rapidly. It's moving out of the pure research labs. So the key takeaway, for me, it's that the quantum age isn't some far-off science fiction concept anymore. It's unfolding now. It's not just a technological revolution, though it is that. It's potentially a revolution in thought, a new way of understanding and interacting with reality at its most fundamental level. The final chapter isn't written, but we now have the principles, the tools, and a growing global community ready to write it.
That's a powerful thought. So finally then, thinking about that secure future we need, will it ultimately rely on PQC, or will QKD be the answer? Which path wins?
I think the answer is clear. The future of a secure world won't be one or the other. It's absolutely going to be both.
Both, okay.
Yeah. PQC is the essential, near-term, scalable solution. We have to deploy it to protect our current vast digital infrastructure from the looming quantum threat. It's the first line of defense, the broad shield. But quantum cryptography, like QKD and eventually a full quantum internet, will likely offer an even higher level of physically guaranteed security for those really critical communication links where the absolute assurance provided by the laws of physics is paramount. They serve different complementary roles in a layered security architecture. We'll need both PQC's resilience and QKD's physical guarantee.
A layered approach. That makes a lot of sense. Wow, what an incredible journey it's been, diving deep into quantum computing across this series. From the absolute basics to steering right into its, well, complex and fascinating future. This final dive really underscores that idea you mentioned, that quantum is a revolution in thought. It really invites you, the listener, to think about how this fundamentally different way of looking at information and reality might change how you see things well beyond just computers. How does redefining computation ripple outwards? Something to mull over. Thank you so much for joining us on this deep dive into the future of quantum computing. We genuinely hope it's given you a shortcut to feeling well-informed and maybe sparked a few ha-ha moments along the way. You can find more of our in-depth discussions on the Tech, AI, and Beyond channel. Please do make sure to subscribe so you can stay informed and dive deep with us again next time.